Yep, thanks for joining us today. Pleasure to have Michael Cantoni as our presenter today. He will be talking about integral quadratic constraints for asynchronous sample data links in his talk. Thanks, Michael.
Okay, thanks, Aman. So, as promised in the abstract for the talk, today I'll be mainly focusing on how to use integral quadratic constraints within the context of stability analysis for feedback interconnections in general, and to provide a bit of context, we'll see how to apply such techniques to analyze systems that involve asynchronous sample data links. So before starting, let me first acknowledge that a lot of the stuff that I'll be presenting today was done in collaboration with Chung-Yao Kao Isaac, who's in Taiwan, and Mark Fabro, who finished his PhD at the University of Melbourne last year. So just to provide a bit of context for what we'll end up looking at right at the end of the seminar, consider a digital network of dynamical systems. Okay, so that's illustrated in this picture here, where these circles represent some continuous time dynamics. So these solid signals coming in and out of these blocks are continuous time signals, and there's some dynamic relationship between those. And these continuous time dynamical systems might interact with each other directly or via so-called sample data links. So what is a sample data link? Well, it's something that will involve sampling in time at the input, discrete in time updates of some sort of interpolator at the output, okay? And in between, there will likely be some digital data encoding, as well as whatever processing is required to transfer the information from one side to the other. So the question is, well, is the network well behaved? So later on in the talk, I'll focus just on these two aspects of sample data links, and because I can say the most about those sorts of things, whereas dealing with quantization and so forth is very much a future challenge, as I'll discuss later on. So really, a system like that is just a big structured feedback interconnection, okay, where we have something that represents the node dynamics and perhaps how that each of those interact with its local environment. There's the links that can be pulled out into a block like this, and something that reflects the network structure. Okay, so the point is that analyzing networks is really just about analyzing structured feedback interconnections. So right at the end of the talk, we'll look at an example that is a very simple case that involves linear time invariant node dynamics, just a single input, single output sample data link, but that link will not be ideal in the sense that the sampling at the input, at the source, if you like, will be aperiodic and uncertain in terms of the timing of sample events. Whoops, I've just lost, I think, that back again. And the timing of updates at the output will also be uncertain and be potentially asynchronous with respect to the sampling events at the input. Okay, so it turns out that sample data links with these sorts of properties correspond to there being an uncertain time varying delay between the source and the sink. So the approach that I'll take is based on input-output methods, and in particular graph separation. So let's just spend some time now thinking about how to analyze feedback interconnections where potentially blocks are uncertain via so-called integral quadratic constraints. So we're going to spend quite a bit of time in this section before then going and showing how to apply such techniques to the analysis of a system that looks like this, right? So we'll see how to write down integral quadratic constraints for sample data links with uncertain aperiodic sampling and asynchronous zero order hold updates. And then we'll look at a simple illustrative numerical example. So, as we've seen, studying networks really corresponds to studying feedback interconnections. There's a well-known, I don't know how well known it is, but input-output approach to the analysis of feedback interconnections that really corresponds to ensuring that the input-output graphs are separated in an appropriate sense. Okay, and this sort of approach dates back to the work of Zames in the 1960s, and you know, people like Charlie Dessau and Vijayasagar also did work in this direction, and you know, they have a quite nice book called Feedback Systems and Input-Output Properties. You know, this sort of stuff was extended in the 80s by the likes of Safonov and Athens. Zames, again, with one of his students, started the work on the gap metric within this sort of context. Vijayasagar, again, contributed to this sort of work. And then in the 90s, you know, Giorgio and Smith, you know, pursued the gap metric type approach. Thiel did some work in this area, and Magretsky and Rancer also did work that is commonly known as the integral quadratic constraint approach to the analysis of feedback systems. And that was building on work of Magretsky's supervisor, Jakubowicz, who also did some important work in this direction. And in the 2000s, you know, people started applying these input-output graph separation type approaches to the analysis of feedback interconnections to study networks. So people like Janis Lestas and Glenn Vinicombe, Ulf Jonsson and Isaac and Fujioka. So this approach is closely related to distributed systems analysis, which differs from this purely input-output perspective in terms of there being some sort of state space and storage functions that are used to analyze the stability of systems. So, you know, work of Willems and Moylan and Hill and so forth. So really all I'm trying to do with this slide here is just put some familiar names perhaps to some of the stuff that I'll be talking about next. So, okay. We're interested in studying feedback interconnections, and that's a lot worried about them being structured for the moment. But a feedback interconnection involves two open loop components. And we're going to take those open loop components to be causal maps that are uniformly bounded when restricted to L2. Okay, so they're defined on the extended L2 space, but when you restrict the inputs to be elements of L2, so finite energy, then what you get out will also have finite energy, and there'll be some sort of uniform bound on the gain. Okay, and in addition, we'll assume that these input-output maps are such that zero gets mapped to zero. Okay, so we say that a feedback interconnection like this, which is really a system that maps some exogenous inputs to the feedback interconnection to the internal signals, is well posed if for every pair of exogenous inputs in the extended L2 space, there exists a unique pair of internal signals, V1 and W2, that are also in the extended L2 space that satisfy these feedback equations. And really this equation, these two equations here are encoding these summing junctions, if you like. And in addition, we would like the mapping from the exogenous inputs to the internal signals to be causal. So that's what we mean by well-posed. Well-posedness is you know, something that's often not too difficult to achieve. In particular, if any one of these has zero instantaneous gain, then the feedback interconnection will be well posed. What we're more often interested in is what happens when these exogenous inputs are restricted to L2. And we say that the feedback interconnection is stable if the corresponding internal signals will also be in L2, with there being some finite bound on the size of the internal signals relative to the size of the signals that we put in. So these are all sort of standard concepts. So let's think a little bit about how a feedback interconnection of the kind shown here works. Well, really what it's doing is decomposing the exogenous inputs into signals that live in the graph of in the graphs of each of the open loop components. So that's illustrated in this figure here. Okay, so this represents the graph of this open loop component. This represents the graph of this open loop component. So the graphs are subspaces of L2 cross L2. Okay, so each point on here is a pair of signals across time. Okay, so if we take a pair of exogenous inputs, that's a point here, then what the feedback interconnection does is decomposes that into something that lives in the graph of H, okay, and something that lives in the graph of delta. And it does so as an oblique projection, okay. Now what I've drawn here makes sense when these things are linear. I don't quite know how to draw these pictures in an informative way when these are non-linear, but you know, I'm not really assuming linearity in anything that I've said so far. Okay, and so the fact that we're decomposing these exogenous signals into things that live in the graphs of the open loop components can be seen directly by just rewriting the feedback equations. And you can see that here's our exogenous inputs and they're being decomposed into something that lives in the graph of delta and something that lives in the graph of H, or actually minus H and minus delta. Okay, and you can see that this number here, okay, you know, will depend on how this oblique projection decomposes the exogenous inputs into internal signals. Okay, so we start off with something of this size, and you end up with internal signals here that are potentially bigger. All right. Now, how big this bound has to be depends on the separation between the graphs, as we'll see on the next slide. Okay, so you can see that you know, if I now perturb the graph of H, say, to get a new graph, okay, then and that perturbation is such that the separation between the new perturbed graph for H and the original graph for delta, then this oblique projection results in something that's larger. Okay, so it seems that, you know, reducing the separation between the graphs requires a bigger K here in this bound that effectively defines stability. All right. And you know, the same works if I perturb the graph of delta in such a way that the separation between that and the graph of H is reduced. Again, I end up with something bigger. So reducing the separation between the graphs, yeah, requires a bigger K here. And in principle, if you reduce the separation to 0, the feedback interconnection will no longer be stable. Okay, in the sense that there will no longer exist this finite gain. All right, so the point I'm trying to make here is that you can understand stability of feedback interconnection from the perspective of how separated the input-output graphs of the two open loop components are. All right, so let's think about how we might verify that the graphs are separated by ensuring that there's some sort of bound here on the size of the internal signals that I get relative to the size of the external inputs. So let's suppose that I've got a function sigma, okay, that is a mapping from L2 cross L2 to the real numbers. And let's suppose that it's quadratically continuous in the sense that for every epsilon greater than 0, there exists a kappa greater than 0 such that this inequality holds, okay? And let's suppose that when I evaluate this function sigma at points that live in the graph of delta, I always get a non-negative number, okay? And that in addition, there exists an epsilon greater than 0, so that when I evaluate this function sigma at points in the graph of H, the other open loop component, I always get a strictly negative number, okay? And let's say that holds for all points in the graph of delta and all points in the graph of H. Now, if we know that the feedback interconnection of H and delta is stable, okay, then we can derive from these two conditions a bound on the gain from the exogenous inputs to the internal signals, okay? So if we just take Y here to be things in the graph of delta, okay, even though this one is the graph minus delta, and X to be things in the graph of H, I could write down this inequality just on the basis of these two conditions holding, right? So this shows that this is non-negative, okay? I'm now going to replace this guy here by this and then add it to this, and so I'll get a minus epsilon times this plus kappa times this guy here when I put Y equal to something from the graph of delta and X equal to something from the graph of H, okay? Then just rearranging this, okay, I can just say, well, all of this is greater than 0. I can then take that onto the other side, gives me this thing here, and I can see that the size of the internal signals corresponding to an input-output pair of H will be bounded by kappa on epsilon times the size of the exogenous inputs that went into the system, okay? You know, that implies this bound when I just choose a different pair of the internal signals, right? So instead of just looking at this and this, if I look at this and this, right? You can still get a bound on the gain from the exogenous inputs to the internal signals that just comes from this quadratic continuity property of this function sigma that is used to define two conditions on the elements of the graph, okay? Now, these two conditions alone are not enough to assume, to conclude stability of the feedback interconnection, right? To be able to write down this, I had to assume that the internal signals are in L2, right? Because you know, this function is only defined on L2, okay? But what these two conditions are giving me is a bound on the gain of the closed loop, if you like. Now that can be exploited to derive this stability result, okay? So this stability result involves those two conditions again, but the first condition is on the graphs of a path of deltas, okay? So now I've got a path of deltas starting from 0, okay, all the way up to delta, and it's just a scaled version of delta. So if I know that my closed loop interconnection is well posed for all values of lambda, okay, which is not a hard condition to ensure, I just need one of these guys to have 0 instantaneous gain, for example. And I know that this constraint holds for all delta along that path. Sorry, I've just lost the thing again. I don't know why that keeps dropping out. then if the other open loop component satisfies this complementary condition, the same as 4, then we can conclude that the closed loop interconnection is stable. Okay, so the way this works is that, well, we know that the closed loop is stable with lambda equals 0 because H is stable, right? So if I've got a stable H here and I put 0 here, no matter what I put in here, the internal signals will be in L2, okay? This will always be 0, right? So this will be whatever W is, and this will be whatever H spits out in response to W plus V, okay, which still gives you 0 out. So we know that at the start of this path, the closed loop interconnection is stable. Now, if this is stable, then the complementary conditions here yield a bound on the closed loop gain, okay? And this bound is independent of lambda, okay? So if you look back here, you know, the kappa and the epsilon here just depend on the properties of sigma, okay? They don't depend on where we're evaluating them, right? So as we vary lambda, I get the same bound here, all right? Okay, so we know that this closed loop gain is going to be bounded and it won't depend on lambda, okay? Now, if we just look at part of this closed loop mapping, okay, and so it's like saying, I'm going to look at this closed loop and I've got lambda here and I know everything's well behaved, okay, and what I'm going to do is add to that a delta, a small delta scaled version of big delta, okay? Then I know I've got a finite, this guy here is stable, okay, as a feedback interconnection, okay? I'm now going to effectively form a new feedback interconnection, all right, where I know that I've got a bound on the gain of this guy here, all right? So intuitively, if I just make this small enough, then adding this loop in will not destroy stability. So that's like a small gain type result, okay? So I know this guy has bounded gain, so I can always choose delta small enough so that the feedback interconnection I just drew is still going to be stable, right? And again, I don't have to choose delta in a way that's dependent on lambda. It's just independent of lambda, all right? And of course, stability of this will imply stability of this, where I've got lambda plus delta as the scaling factor here, right? So it's just corresponds to now absorbing this into here. Okay, I can add that in there and I just get lambda plus delta times big delta. All right, so we can conclude stability of the feedback interconnection H and delta by starting off at 0. We know that that feedback interconnection is stable, okay? And this argument here shows that we can just proceed along the path starting from lambda in steps of delta until we get to this one here, right? And effectively, these two complementary conditions are ensuring that the graphs always remain separated all the way along that path by an amount that is effectively independent of where you are along the path, okay? So this is the so-called IQC robust stability result, okay? Involves a condition on one open loop component and a complementary condition on the other open loop component. And when those conditions hold, you can include stability of the feedback interconnection. All right, so it may not be clear to you up to this point why the term integral quadratic constraints is used, because the only property we've used so far is this one here. Now, how do we find such functions sigma? Well, if I've got a bounded linear self-adjoint operator pi, okay, and I form the function sigma in the way shown here, then it turns out that the mapping from x to sigma x will have this quadratically continuous property that was exploited to get the uniform along the path bound on the gain here as required to make this argument. Okay, and you can see that this involves the inner product of L2. This is like a quadratic form, and the inner product involves integrating across all of time. So that's where the terminology integral quadratic constraints comes from. Okay, and basically pi can be any bounded linear shifted linear self-adjoint operator, but some ones that are commonly used shown here. So one looks like this. Okay, so if I take pi to be just this multiplying signals by a constant mu, okay, in this matrix form, then I'll get a small gain type constraint on the operator that defines x, which will be an element of the graph of that operator. Okay, and similarly, passivity corresponds to taking pi in this form here. Okay, and in fact, the sorts of integral quadratic constraints that we'll use later on when analysing sample data networks will only use a small gain and a passivity one combined together. Okay. All right. So you may be wondering, how does one go about verifying conditions that look like this? Okay, and the way that this result is applied is that you'll devise a integral quadratic constraint that covers your delta, which might be some sort of uncertain object, and you then verify stability by testing this condition. Okay, and it turns out that testing a condition like this is computationally tractable if the object H is linear time invariant. Okay, and that follows from the KYP lemma, okay, which says that there will exist an epsilon such that this integral quadratic constraint holds with the operator H being a linear time invariant object with a transfer function as shown here, if and only if there exists another epsilon such that this linear matrix inequality holds. So in principle, you can test feasibility of this linear matrix inequality by solving a semi-definite program. Okay, so in the case that H is linear time invariant, testing a condition like this boils down to solving a convex program of finite dimension. Okay, so in principle, you can do it, but it relies on the H being linear time invariant. You can analyze the performance of feedback interconnections, not just stability, using integral quadratic constraints. So you might be, in addition to knowing that this feedback interconnection is stable, you might be interested in knowing that the gain from this exogenous input to this performance output is bounded in some way, and that corresponds to simply just using a that can be done by using a sort of a bigger integral quadratic constraint in some sense. Okay, so we've got this characterization of delta expressed as an integral quadratic constraint. If there exists an epsilon such this complementary quadratic constraint on H is satisfied, then the interconnection will be stable and the gain from here to here will be bounded by gamma, which appears as a parameter in this complementary condition. Okay, so again, testing something like this corresponds to verifying feasibility of LMI, which in principle is can be verified by solving a convex program. So just to summarize the typical approach to using these sorts of results, you encapsulate the input-output behavior of delta with an integral quadratic constraint. Okay, so it's something that we denote like this. And then we verify the complementary condition on H by solving a convex program. Right? Now, often the integral quadratic constraint used to encapsulate the behavior of delta is something that's parameterized, and verification of this condition involves finding a parameter such that the complementary condition holds. Okay, and the challenge is to reduce how conservative you're being by devising a sufficiently rich family of integral quadratic constraints for delta. So how might we go about, generating a sufficiently rich family of IQCs? Well, if we know that we have that our delta satisfies an IQC defined by the multiplier pi k, and that is true for n different multipliers pi k, then delta will also satisfy this integral quadratic constraint defined by a multiplier that is constructed from the individual multipliers in the way shown here. So this is showing you, for example, how you might end up with a parameterized family. Okay, where the parameters will be xk in this case. And so verifying this complementary condition will be about finding an appropriate xk such that this condition holds. And often that corresponds to a quadratic, a convex program again, in the sense that those parameters often appear here, and so this is still a linear inequality in the parameters. And when dealing with structured interconnections, you can construct IQCs for the structured object from individual IQCs as shown here. So if I know delta 1 satisfies this IQC and delta 2 satisfies this IQC, then I can construct an IQC for the structured object delta consisting of delta 1 and delta 2 as shown here. Okay, so there's lots of tricks for building this sufficiently rich family of IQCs. The more IQCs you have, the less conservative your analysis will be. Of course, these are just sufficient conditions, right, for stability. And if there's going to be lots of deltas that satisfy this constraint, not necessarily just the ones that you're interested in. Okay, and so you want to use as many constraints as possible to make their intersection, if you like, as tightly packed around the thing that you're interested in as possible, right? But this is a robust stability result because this will be stable for any delta that satisfies this one, including the ones that you're interested in. All right, so I don't know, maybe before I go on, are there any questions on IQC analysis? Maybe, I don't know. No questions? Okay, all right, I'll proceed. All right, so let's now go back to this sample data problem and think about how we might devise integral quadratic constraints that encapsulate the sort of sample data links that I mentioned at the beginning. So things with uncertain aperiodic sampling at the source and asynchronous zero hold updates at the sink. So here's a sample data link. Okay, there's the source, the input. Okay, that gets sampled. Somehow that's transferred to the sink, the output of the link, where it goes through some sort of interpolator to produce the continuous time output. So let's just think of that interpolator as a zero order hold. Okay, and I think it's profitable to not just restrict your attention or your thinking to this transfer process being some sort of communication link necessarily of the kind that like a Wi-Fi link or something like that. I mean, it could be as simple as a buffer, right? And the asynchronous between the output and the input might arise because of the mechanisms used to read the buffer, become aware of when there's something in there, and so forth, right? So I think this is needs to be thought of as as a very general picture, not just Wi-Fi links and so forth. Okay, so in the case that the activity on this side that produces the output on the basis of samples that have been transferred from the input, when that's synchronous and the sampling is periodic, so there's no real uncertainty associated with this link, then the link works as shown here. So this is the continuous input in black. Okay, it gets sampled at these times marked with a prime. Okay, the separation between those times is constant. Okay, it doesn't change. And what's produced by the output, whenever there's a sample taken, the output's updated to the value of that sample and held there until the next sample is taken, and then the output's updated and held constant until the next sample is taken, and so forth. You can think about the behavior, the input-output behavior of this in terms of there being a time-varying delay from the input to the output. Okay, so what's coming out at this point in time is the value of the input that amount of time into the past, right? So the amount of time into the past that you have to go to find the value of the input appearing at the output is something that increases with time, okay? And every time a new sample happens, assuming that gets, the output is updated straight away, okay, that delay gets reset. Okay, so when this new sample comes in, the output's updated to that, the delay goes back to 0, and then it increases linearly with a slope of 1 until the next sample occurs. Right, so you get, it's an unfortunate choice of notation, but anyway, there it is, sigma. It's not the same sigma as before. Okay, you can think of the input-output behavior of the sample data link that is, in this case, periodic, with a synchronous 0 order hold at the output as being a time varying input delay of this many time units, and that is a sawtooth function that periodically resets to 0. So what happens if there is some uncertainty in the timing of samples at the input and updates at the output? Well, what happens is that you still get a time varying delay from the input to the output, but that time varying delay no longer resets to a constant value. So that's illustrated in this figure here, where the primes correspond to times where there's a sample event at the input, and star corresponds to an update of the output. Okay, so you can see here that at a sampling time, okay, you don't necessarily get an update of the output straight away. Okay, that happens sometime later. So what you're getting at the output is still a delayed version of the input. Okay, and that delay will increase linearly with a slope of 1 until there's a new update of the output, okay, that changes the output because there's been a sample in between. Okay, but what happens is the value that the output is updated to at this point in time is not the value of the input at that time, but of some time in the past. Okay, so it's like, something gets written into a buffer every time there's a new sample, but this guy doesn't look at the buffer all the time. It doesn't look at the buffer every time there's a new sample. Okay, and it takes some time for it to see it. Okay, so what happens is that the update events of the output no longer correspond to the delay being reset to 0. It resets to some value, which will be non-zero. It could be 0, but it's not necessarily 0, before the delay starts increasing again until there's an update event at the output, right? It changes something, and then the delay is reset to some value, in this case 0, because there happened to be a sample event at that same time. So under uncertain aperiodic sampling at the input and asynchronous hold updates at the output, you still end up with this sawtooth-like delay, except it doesn't reset to 0. And the amount of time it spends increasing will also vary with time. So the characteristics of this delay function really correspond to how far apart can these things be, and how big can the value to which it resets be. Okay. In principle, the biggest delay you could get will be the sum of these two things. Okay. So what might we use to bound those two times which characterize this sawtooth delay that doesn't reset to 0 intermittently? Well, it turns out that you can bound this amount of time by a bound on the maximum time between sample events, plus a bound on how long you might have to wait for the output to be updated after a sampling event. Okay. And this amount of time can be bounded by this time is bounded by anything that bounds this. Okay. And this is really a measure of how stale the sample is by the time a sample that results in an update of the output is by the time the output is updated. Okay, so these are characteristics of the sample and hold event sequences. Okay, so if you can bound these characteristics of the sample and hold event sequences, then we can bound these times, which, if you like, are characteristics of this sawtooth time varying delay. All right. Now, getting back to IQCs. All right, how might we use the IQC framework to analyze a system that involves input-output mappings of the kind we just looked at? Well, it turns out to be difficult to find the integral quadratic constraints for this mapping as it stands. Okay, so you know, what I'm going to show now is an example of a so-called loop transformation. Okay, so I'm going to convert this input-output mapping into a new one for which some integral quadratic constraints can be written down. Okay, so this link looks like this. It looks like an ideal link, right? And this, if you like, characterizes the error relative to an ideal link. So just a direct connection from the input to the output. And what I've got here is something that takes derivative with respect to time. Okay, so I need smooth inputs into this thing here, which you usually have because you have some sort of anti-aliasing filter before sampling. And then that's kind of undone by this integrator here. But the object that we're going to write down a IQC for is this object here, not the whole thing. Okay, and we're going to apply this loop transformation, this closing of the ideal link when studying a feedback interconnection that involves the sample data link. All right, so it turns out you can see here that this object is this time varying delay. Okay, but the delta that we're going to characterize with the quadratic constraints is not just the time varying delay, it's the error relative to an ideal link, but only after we've integrated something. So that gives us a delta that looks like this integral of what's coming in, okay, from some time in the past up to the current time, okay? And these lambdas here correspond to the most recent sample, okay? The thing that the output will be updated to when there's an updated event, and the interval here that's used to define this operator corresponds to the distance between update events at the output that result in a change. Okay, so this object here is this funny integral operator, and it turns out that you can write down at least two IQCs for an operator that looks like this. Okay, based on these sorts of bounds for the sample and hold update sequences. Okay, so the first is like a bounded gain IQC. Again, The first is a bounded gain IQC. Okay, and you can see that the bound on the gain of this integral operator is in terms of the bounds on the intersample interval, how long you might have to wait for an output update after a sample, and how stale the sample might be at an update event that changes the output. Okay, so this number here is less than the maximum possible delay. Remember, the maximum possible delay would have been the sum of this, this, and this. I don't know. Can you not see my pointer anymore?
When I think the pointer, when your pen is away from the surface, it doesn't show anymore.
I don't know. I keep on losing the connection. Is the problem? Is it back? Yes. Okay. So this is not just the maximum delay; it's less than the maximum delay, and it's really derived by exploiting the special properties of this integral operator. You can also show that this passivity-like IQC holds. Okay, and that depends on how stale the sample might be that produces a change in the output. Okay, so these are two IQCs. I don't want to go into the details of how they come about. It's a bit technical, but as we saw before, you can combine IQCs to find a new IQC. Right, so this is showing how to combine the bounded gain and the passivity one into one IQC. Okay, and it's now parameterized by these parameters X and Y. Okay, so we've got this parameterized family of IQCs that characterize the delta. So let's look at how we might apply such a characterization of an asynchronous sample data link to study a feedback interconnection. So let's consider just a simple example. So I've got a plant, okay, and here's my sample data link. All right, and I could model this sample data link, which is a depth 1 buffer that's overwritten every sample, but it's read with variable delay. And by reading with variable delay, we may not see every sample, so some samples may be missed. Okay, but we're assuming that it's every sample gets written into the buffer, and the other side may see it, may not, and how long it takes to see will be varying. Okay, and that can be modeled as this composition of sample and hold operators as shown here. F is just an anti-aliasing filter, which is required to make this bounded, and it's also required for this to be well defined. Okay, so what we're doing here in this bottom figure is closing the loop with an ideal link. So I'm closing the link with the like pretending this is just the identity. Okay, and then what I'm left with is a delta at the bottom. Right, so this just corresponds to this picture here. All right, so that's all I'm doing. This is your loop transformation. So I'm closing the loop ideally, and then using this to represent the difference between this and the ideal loop. Okay, and the object we're left with here is this guy here. All right. So within the context of the IQC setup that I showed you before, this is like the H, right? And this is your delta. And we've just seen how to write down IQCs for your delta. These are the bounds. Here's a bound, let's call it H, on the intersample interval, okay? And I'm going to parameterize, how long you might have to wait for the output to be updated and how stale the sample could be relative to H via this parameter delta. Okay, so delta, if you like, reflects the level of the degree of asynchrony between the output and the input. So, verifying stability of this interconnection involves verifying that the complementary IQC is satisfied by this H, right? So this H here, these are all LTI objects. So it'll just be some LTI object, and I can verify that it satisfies an IQC that is complementary to the IQC that characterizes delta by solving a convex program. all right? And these are the results you get, okay? So as we vary delta, the degree of asynchrony, right, we get a decrease. As that increases, we get a decrease in the maximum verifiable intersample interval, which was represented by H. Okay, it's not surprising. Okay, if you're wondering how conservative this is for this plant with a constant gain of one feedback loop around it, well, with a filter in there, we'll have a phase margin of about 85 degrees, and from that you could work out what the maximum constant delay based on the phase margin is, and it's a number less than we can verify here. Well, the thing we're studying here is not just a constant delay, it's a delay that resets to zero or resets to a lower value sometimes, okay? All right, so nothing surprising here. You can verify a bound on the closed loop gain that you get, okay? And so this shows how the bound on the closed loop gain that you can verify, and remember these are just sufficient conditions, right? So this is conservative, varies as you change the degree of asynchrony and vary the bound on the intersample interval. Okay, and not surprisingly, as those numbers are small, you get the best gain, and as those numbers get bigger, the bound that you can verify and the closed loop gain gets bigger. All right. And this is probably the more interesting one, which shows that for certain transfer functions for the plant, having the bounded gain and passivity IQC together is important. So it turns out that for this example, having the passivity IQC as part of the description of the system doesn't make any difference. You get the same results if you just use the IQC corresponding to this, right? Which would translate to setting Y equal to 0 in here, all right? But if you change the plant transfer function, then it turns out that both matter, right? So this is showing what happens for having both the bounded gain and passivity IQC in place, right? So, and the red one here is when you take out the passivity one, right? And you can see when you take out the passivity one, we can only verify a smaller value of H compared to having the passivity one in there, okay? And how much of a difference it makes depends on the location of this non-minimum phase 0, okay? So I guess the message I'm trying to convey here is that, it really is important to have as many IQCs as possible, okay? This is just 2. I'm sure there are others that could be written down. But I guess the purpose of this example is just to illustrate how you might use these IQC type techniques. So to wrap up, some outstanding challenges relate to dealing with realistic, within the context of these sample data networks, relates to dealing with realistic quantization in the links, okay? And by realistic quantization, I mean things that saturate, okay, and that don't have an infinite number of levels at 0, okay? So you can get these logarithmic quantizers for which it's very easy to write down integral quadratic constraints, okay? But they're not, logarithmic quantizer is not very realistic. You can't build one, it's got an infinite number of levels, right? So how to come up with IQCs for, realistic quantizers, including ones that zoom in and zoom out, so things with dynamics, is an open challenge. Also, leveraging network structure in the analysis, right? So in this simple example, where are we? We only had one link here, but in the network case, we've got structure here, we've got structure here. How can that be exploited in the analysis? I think that's an open challenge. Although, some of the work that I mentioned done in the early 2000s may be relevant. And again, there's a question of, when verifying the complementary condition for H, when you solve a a semi-definite program, that's likely to be very structured. And is it possible to exploit structure in solving that SDP? So you can deal with very large networks. All right, so that's it. So we've looked at stability analysis of uncertain feedback in connections via integral quadratic constraints. This is an input-output method, and I guess part of my motivation for spending so much time on it today is I think that it's overlooked by many people who tend to focus on state-space modeling. But I think there's a lot to be gained, especially from an analysis perspective, by first looking at the problem from a purely input-output perspective. And I think that's particularly relevant to these sorts of challenges. Then we saw how to use this approach to study systems with sample data links that are uncertain, in the sense that the timing of samples at the input are aperiodic, and for which we may only have a bound on the intersample interval, and where the activity at the output of the link is asynchronous relative to the events at the input. And we saw a numerical example. So the details of the numerical example can be found in this paper on arXiv, which was just recently accepted for TAC. So thanks for your attention.
Okay, any questions for Michael?
Can you hear me?
Yep.
Oh yeah, I want to ask a question. So is it hard to state these IQCs for a more complex interconnection, or it follows the same procedure?
What do you mean by complex interconnection?
Maybe you have a more topology on the links or things like that.
Well, that goes back to this.
Without exploiting maybe the structure, just as it is.
Right. So, when you've got a network, right, you end up with what's effectively a very structured feedback interconnection, where the open loop components have a lot of structure. So here, these are block diagonal, right? And there'll be some structure in here, right? And so the question relates to the point that I was making at the end, right? It was when we're devising IQCs, right, that describe these structured blocks, can that structure be reflected, in the IQCs, so that you're not being super conservative?
Okay.
Right? Or are there ways of exploiting that structure to build up a big IQC for the structured object from little IQCs, right? So that's relates to this sort of thing here, right? Where you can construct big IQCs for a structured object, an IQC for a structured object out of IQCs for the components, right? So this is easy when it's block diagonal, but what if you have other structures?
Yeah.
Right. And then you might be able to do this, but then verifying the complementary condition for where are we? So that's about building up these, right? And so that'll define a certificate that has to be verified, right, for the H block. And if that H block has structure, can that structure be exploited in some way to make verification of this condition scalable or something like that? But I don't, I don't know the answers to all these questions, right? But that's the, I'm pointing to those as outstanding challenges at the end, right?
Yep. Okay. Thanks.
But in principle, I think this input-output perspective will facilitate coming up with, good answers to these challenges.
Okay, thank you.
Make sense? Yep.
Yep. Yep.
Hey, Michael.
Hi.
So is your sampling and interpolation system infinite dimensional? And if so, is this a good method for dealing with infinite dimensional systems in general?
well, it's a delay, time varying delay, right? So a delay is infinite dimensional, if that's what you mean.
Yes.
Yeah. So the signal spaces. Where are we? So these L2s at any time. So W evaluated at a particular time will be finite dimensional. Okay. But the state space for these objects, for this object in particular, could be infinite dimensional. Okay. Right? If you were to write down a state space model for it. But I guess the point of this approach is that it doesn't require you to necessarily have a state space description of the system.
Cool. Yep. Understood.
Right. But within the context of the sample data example, yeah, this object has an infinite dimensional state space, right? Because it's a delay. And it's, to make things worse, it's a time varying delay. And what we're trying to do is in describing delta, right? In encapsulating delta with a constraint, right? That will hold for not just the deltas you're interested in, but potentially many others. We're trying to make sure that we're capturing as much of what we know about delta in this constraint as possible to reduce how conservative our analysis is. Right, so we're trying to exploit the fact that it is this sawtooth delay that resets, right, which is reflected in the structure of this integral operator representation of the delta that we're interested in within the context of sample data links. Does that make sense? And it's infinite dimensional. You can see you're integrating into the past, right?
Yeah.
So it's not, you need to know a chunk of things into the past.
Cool. Yep.
Okay, let's have one last question. Farhad wanted to ask a question.
Michael, now if we don't have any buffer and the packets get reordered, would it be possible to find an IQC for that, or it becomes hard because if you discard all the packets, the delay can become potentially infinite for them?
So this allows packets to not make it to the other end, right? But something eventually happens, right? So there may be things written into the buffer that get overwritten before they're read. So you can lose stuff, right? But we're, effectively assuming that things don't end up going out of order, right? But it is possible to do analysis of this kind for situations where, there's no time stamping, and so the time varying delay with which the output becomes aware of a new sample is such that things get reordered. You can do similar analysis, right? It's in Mark's thesis.
Great, thanks.
Yeah, but it's not that things it's not like the delay is ever infinite, right? It's just some samples are never seen at the output.
Yeah.
Right, but something is always eventually seen at the output. And the delay associated with that will always be finite. So, let's say I get a sample, it's written in, that one's not seen because it's overwritten by another one, right?
And you only consider the one that you see. Yeah.
You only consider the one that you see. So the delay is always finite, even though not all samples are seen. Does that make sense?
Yep. Yeah. Thanks.
Okay. Thanks, Michael, again. Thank you, Michael, and thank you for all of your attention. See you next week for the next talk.
All right. See ya.